Meglio che posso, ovviamente appunto volevo semplicemente capire se erano prevalentemente studenti, prevalentemente, poi immagino tutti insomma in area comunque fisica o no?
Sì,
Con-
è stato segnalato anche a Geology,
Ah, ok.
sicuramente.
Beh, vabbè, la cosa buona è che appunto è comunque un argomento abbastanza multidisciplinare, quindi insomma
Sì, io
tutti
anche un
quanti.
gruppo di chimici che fa astrochimica, l'ho segnalato.
Ok, sì, perfetto. Sì, ho visto
La
insomma
Nadia,
Nadia
magari.
Balucani, sì, sì, la conosco, come no, certo. No, 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 infatti, no, infatti la cosa buona è che è sempre un argomento che comunque include tutti e la cosa brutta è che tutti quanti nel loro campo sanno molto di più di quello che so io, perché ognuno, i
Ho
geologi,
capito, sì, sì.
capito? E quindi, quindi vabbè, alcune cose saranno ovvie per alcuni, però va bene, ecco, questo è il bello.
Questo è il bello, no?
Infatti, sì, sì, assolutamente sì.
Parlano, penso sì.
Allora, aspetta un attimo, un po' se Monica mi conferma, comunque iniziamo. E andiamo sempre in inglese.
Sì, ok.
Monica ha già iniziato, quindi sì.
Oh,
Magari aspetta, tutti i partecipanti. Yes. Everybody who is not the speaker, please mute yourself.
yes, please. So, we can start. Welcome to everybody. This is the second talk of our new series of seminars of physics, and we have Amedeo Balbi. Amedeo is associate professor at University of Roma Tor Vergata in astronomy and astrophysics. He's, I would say, a cosmologist as a background. So he has interest in the physics of Big Bang, dark matter, dark energy, and so on. But he's also moved to astrobiology, which is an interdisciplinary field of study. I don't really know the definition, but it has to do with the concepts of life in the universe, searching for life, or the concept of habitability, and so on. He will talk about this. He is also a popular author of science books. So I hope we will enjoy his talk. So, Amedeo, you can start.
Okay, thanks. Thanks for the invitation, first of all. Thanks for the introduction. And yes, I will try to give an overview of what an astrobiologist is supposed to do, which is basically to deal with the problem of life in the universe, which of course is a very big problem. And one can approach from this problem from coming from different disciplines. And as Nicola was remembering, I was reminding, I originally I'm a cosmologist, so this was my background for more than 20 years. But in the last, I would say 5 or 6 years, I moved entirely to astrobiology, and so this is the thing that I would like to discuss today. So the overall idea behind this talk is, first of all, to give a really broad overview of what astrobiology is about, why it is interesting, and what people are doing in this field. And the second part will be about some more detailed and specific results. But of course, let me stress and let me emphasize one very important thing to begin with, that astrobiology is a very complicated enterprise, and it's also very multidisciplinary, so that everybody is very competent in one particular subject and everybody sees the problem from that perspective. But then eventually we have to put together all these things, and this is on one hand is the exciting thing, and on the other hand is the very difficult thing, as you will see. So first of all, let me explain what is astrobiology. And as Nicola said, is not always clear what astrobiology is. So I will give one definition, which is a broad definition that is, I would say, almost universally accepted, that says that astrobiology is the interdisciplinary study of the origin, evolution, and distribution and future also of life in the universe. So we live in a big universe, and we have a broad framework about the evolution of the universe. What we are trying to do, and what actually drew myself to this field from cosmology, is precisely the fact that the universe is just one, and everything is happening in the universe according to the same laws, and we understand these laws in general. We understand very well what happens in the universe during its evolution. And one thing that I always say is that, for example, if you were a cosmologist and you never saw a star, but someone gave you the initial conditions of the universe and told you that there were fluctuations in the beginning, and then gravity formed structure and so on and so forth, you could very easily or almost precisely predict that stars would appear in the universe, even if you didn't see anyone. But in this general picture, life is a much more complicated problem. And we know that life appeared in the universe, at least in one case, which is our case. But we are not able yet to say whether this is a common outcome of the evolution of the universe, or it's just a fluke. Okay, there are many people who think that, of course, I mean, since the basic physics is everywhere the same and chemistry is everywhere the same, then life has to be everywhere. But you can also have a different approach and say, well, we are here and we have a bias, so to speak, and we would be here even if it was an improbable event. And so we really have to look and see how things are in the universe. We cannot be sure of the existence of life just based on speculation or statistics. So what are the reasons why astrobiology now is very interesting and is a very active field of exploration? I would say that there are different reasons, but here there are some of them. There are both experimental milestones and theoretical issues that are open. Of course, the theoretical issues are very large. What is life? What is habitable? And how we can remotely detect life elsewhere in the universe. And then there are reasons that come from biology, from the discovery of life forms that can thrive in very difficult environment on Earth. So we changed our perspective about how life can survive in difficult environment. Then there was a very important milestone that we will see in a moment, the discovery of exoplanets. So we know that there are planets around other stars. And then we learned many things about the solar system and other planets in the solar system with exploration and so on. So there are all these directions, all these lines of investigations are converging in the same direction of giving us some very important reasons to understand these things better, both experimentally and theoretically. And so let me focus on one specific aspect. So most of what I would say today has to do with habitability. As I said, I mean, astrobiology is very broad, it's very complex, so one has to look at some specific things and focus on some specific things. And one of the things is trying to understand what makes a given environment suitable for life. And this is a huge problem, of course. And it's a huge problem. We don't understand all the issues here, but we can start from something very simple. And the very cartoon-like picture that we can give is that in order to have life, as far as we know, as far as we learned from Earth, in order to have life, you have to have at least 3 ingredients. And these 3 ingredients are energy, or to be more precise in physical terms, free energy, so energy that can be used to do some useful work. Then you have to have some chemical elements, and in particular complex molecules or organic molecules, so complex molecules based on carbon, to do all the things that life can do, in particular replication, information, and so on. And then you have to have some solvent, which we believe it is water, liquid water. Okay, all these three ingredients, when combined together, given some appropriate physical chemical conditions, will make an environment suitable for life, which doesn't mean that life has to be there. In fact, it just says that we believe that if we miss some of these elements, some of these key ingredients, it is very, 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 very difficult that life can exist. And note that on the right of this cartoon picture, there is also a bottleneck, which is you probably have to have some very restrictive conditions to have what we call abiogenesis, so the beginning of life from chemistry, and so to have the first organisms, you have to have some very specific conditions that we don't know exactly, of course. We don't have a general theory of the origin of life. But then it seems that once the conditions are matched, are reached, and you have life, then life is very adaptable and can actually live in very different environments and can spread around and can adapt. Okay, so probably the general condition for habitability once life is there are less restrictive than the initial conditions, so to speak. Okay, so this is important, not because we understand anything, and in fact the thing is much more complicated than this. And let me go, if I can, to the next slide. Okay, sorry. This is much more complicated than this, as we will see in a moment, but the point is that we believe that we can start looking around and not looking everywhere just randomly, but looking only in places that are more interesting for life.
Okay. So looking nel senso lucky.
No, I said looking, but yeah, not lucky, looking. Looking in specific places, so we want to look in specific places, not just around randomly. And based on what I said in the previous slide, there are some places that are better than others, which doesn't mean that there is life, certainly, but they can be better than others. And these places are places where there can be the combination that I said before, and in particular liquid water. So you probably know that there is this definition of circumstellar habitable zone, which is the zone around the star where the temperature can in principle be in the range that can allow the presence of liquid water. So this is the general, the starting point, the general starting point. When we look around in the universe, we generally start by looking at places where liquid water can be. And this is a graph that tells you what is the distance given a certain kind of star where you can have these conditions. But of course, as I was trying to say, things are much, much more complicated than this, okay? So it's not just the distance from the star, as sometimes is said. It's much more complicated because you have other factors that have to do both with astronomy and with the planetary conditions. And here, again, there is a scheme which is very complicated, and I won't go into all the details of this, but this is just to give you a clear, immediate impression of how things can be approached and how difficult it is to have a general approach to this problem, okay? And in fact, if we look at the solar system, what we found is that there is only one planet which is habitable and inhabited, as we know, and there are two other planets that in principle fall in the circumstellar habitable zone, but they are not so hospitable to life as one would imagine, okay? Because there are other reasons why these planets are very bad for life. Of course, we don't know for sure that there is no life. Actually, we are actively looking for life on Mars and perhaps even on Venus. So we don't know. The case is not closed, but certainly what we can say is that things are much, much more complicated there than we would just expect based on the habitable zone that I showed before. Okay, so this is just to give you a word of caution that have to be used every time we look for other planets. And also the other thing is true, the opposite is true, that there are places that are outside the habitable zone that may be habitable. And for example, there are places like the icy worlds, the moons of Jupiter and Saturn, that are, we know now that they have oceans under their surface, and probably they have some active heat and energy in their core, and there may be even volcanism and availability of complex molecules. So in principle, in these places, there are all the elements that we need for life. So you can actually go beyond the habitable zone and find other places that we wouldn't imagine some decades ago where life could be, but now we know that it may be. Actually, there is also this paper that we published some years ago where we were making some tests in laboratory whether there are organisms that can survive in these conditions. We simulated these conditions of the icy moon in the laboratory, and we showed that in principle it's not impossible to have organisms living in these conditions. Okay, so and there are many other works on this, and this is just an example. Okay. Now, of course, I mean, I was talking about exoplanets, and the big discovery of the past 25 years is that there are other planets around other stars. Here you see the number of exoplanets discovered over the past 3 decades, essentially. The first planet was discovered in 1995 around a normal star. And you see that there is a steady increase and that there are many of them. And actually now we are at over 4,000 planets discovered around other stars, and there are many to come. Now there is this other experiment called TESS, which has, I guess, just released probably more than 2,000 new candidates, and there are many more to come. So I mean, in the next few decades, we will probably discover tens of thousands of exoplanets. Some of them are in the habitable zone of their star, and so we can actually start making some statistics of what these potentially they are not habitable for sure, but they are potentially habitable planets, meaning that you can rank them by some sort of metric and decide whether they have or not conditions for life. As I said, again, I want to be very clear on this. We know very little about these planets. We know that they are there. We know their mass. In some cases, we know the radius. We can estimate the density. We know the period, but we don't know many of the details that we would need to know to characterize actually their surface and their temperature and their climate and so on. So it's really a work in progress. What I'm saying here is that there are some places where in the next few years we can look better, and we want to look better because they are close to the Earth, close in terms of astronomical distance, of course. I mean, there are tens of light years from Earth, but we can study them with the telescopes, and we can characterize their atmosphere, and so we can build models of their climate. And actually what we would like to do in the next decades is to put together all these elements and perhaps also observe directly the light that is absorbed during the transit of the planet by the atmosphere, to find out what is the composition of the atmosphere. And also, and so if we know the composition of the atmosphere, we have much better climate models that we can build. And again, this is another area of very multidisciplinary, a very multidisciplinary area, because we have to talk to climate scientists and, and put together many competences. But what we want to do is to build climate models to know what actually the temperature is, not just based on the distance from the star, but actually from the chemistry of the atmosphere. And if you know this, you can also make another step forward, and this is even farther in the future, but we are preparing to do this, which is to study what happens in the atmosphere when there is life. Of course, we know that life is just a physical process, physical-chemical process, and there are some processes that are not biological that can alter the atmosphere of a planet, and there are processes that come, for example, from geochemistry, and they can alter the composition of the atmosphere. Then there is photochemistry and so on. So there are some processes that don't involve life, where you have some balance on the atmosphere, but then there are processes that are based on life that can have different effects on the atmosphere. One clear example is photosynthesis, that is a physical process where the organisms release a lot of oxygen in the atmosphere, and then you may have other processes like that. Even, but this is again even more speculative, even alteration coming from more advanced forms of life, for example, by technology. And I won't mention this in this talk, but just quickly let me emphasize that there is now a really interesting research work done by many people in the world studying this thing, how technology can have effects on the atmosphere of a planet that you can observe from abroad. Okay, think about what we are doing to our planet, and think what could be the signature of this from remote distance. Okay. But in general, what we want to do is to look for biosignatures, so signatures that are related to the presence of biological activity in a planet that can alter the atmosphere. And the typical example of this is, it's a very simple example, and there are many exceptions, and many other more complicated examples, but a simple example is you have a redox couple that shouldn't be in equilibrium in the atmosphere. It should disappear on a very short time scale. And if you find that, it may be that there is some disequilibrium that can be produced in principle by biological activity. It's not the only explanation, of course, but it can be produced by biological activity. So, for example, if you think about oxygen and methane, on Earth, this is produced by biological activity, not exclusively, but it is produced by biological activity. It's complicated. Things can go very wrong. You can have false positives. You can have all sorts of things. So that's why we have to study these things before interpreting the observations. But the observations will be made. Okay, in the next 2 decades or 3 decades, there will be observatories doing exactly this kind of study on the spectroscopy on the spectral signatures of other planets to find what's there. And so we have to prepare to interpret these observations. Now, this was, as I said, a very, very, very broad overview. I mean, there are many, many more arguments, and it would take forever to go into details. In the second part of this talk, I would like to give some examples of work that I've been doing with my collaborators on some specific aspects. And they, of course, don't cover all the possible aspects. It would be impossible, but we focused on some of them. And in particular, I want to show something which I think is interesting, and it's also, in a sense, is novel. It hasn't been studied in the past, which has to do with the different concept of habitability, not just planetary habitability, but galactic habitability. What does it mean is that we live in a galaxy where there are stars, and not all the locations in the galaxy perhaps are suitable for life in the same way. There may be regions in the galaxy, and I will show you in a moment what it means, but there may be regions in the galaxy where habitable planets can be more common than others. It may be easier to find some places where there is life in some parts of the galaxy. And this is not just true in space, it's also true in time. There may be epochs in the history of the galaxy where life is more is easier to be found. Okay. So I want to show what does implies. Here there are a bunch of works on these topics that I've done with my collaborators in the past few years, and I will give you some highlights of this. But the basic idea behind the galactic habitable zone, and again, there are many theoretical works that have been done in the past 20 years on this concept. Basic idea is that we are here, the sun is here, where the arrow is pointing, and then the galaxy has very different conditions everywhere. There are gradients in, for example, in the abundance of elements, and also in the density of stars, and so on. And so these studies argued that if you look into at least a couple of factors, which is the metal enrichment of the interstellar medium. So you know that astronomers call metal everything which is not hydrogen or helium. Okay, so metal means heavier and heavier elements, essentially. So if you look for these elements that are produced by stars in nucleosynthesis, they are not diffused everywhere in the same way, because you need stars to produce them. And the other thing is that there are events that are potentially catastrophic for life. For example, if you have a supernova at a few light years exploding, there are certainly biological effects. If there is life, it won't be good for life to have a supernova exploding at 5 light years, for example, and even worse for gamma ray bursts. Okay, so you want to be sure that you are in a region where the rate is low of this catastrophic event, but at the same time where you have metals to do chemistry, to do interesting chemistry, and also to build planets, because in order to build planets, you have to have heavy elements. Otherwise, you just have, if you only have gas, you don't have rocky planets. So metallicity can be correlated to the formation of planets. There are models, both theoretical models and also observations that show that there is some amount of correlation between the abundance of planets and metallicity. And so the basic idea is that if you have too many heavy elements, you produce too many big planets, and these big planets are bad for smaller planets. But if you don't have enough heavy elements, you don't produce rocky planets. So you want to be in a soft spot between the two. Okay, so you can build the probability distribution of where you find the best metallicity environment. And the other thing is, as I said, you want to be in a region where the density of harmful events is low enough. Okay, and so all of these points in the same direction by pointing to the fact that probably the inner region of the galaxy is too crowded, and the outer region of the galaxy is better. So we are in a peripheric region of the galaxy, as we know. But if you go too far away, then there is not enough metals there, because there are not enough stars, and so you don't have enough planets. So you want to be in between these two regions. Okay. Of course, there is a huge uncertainty about all of this, but we want to understand things better, and so we try to have some fun with that. Sorry, but I hear something. I think that there is some microphone open. Okay. Good, thank you.
Okay.
Okay. So, as I said, you want to be in a region where you have all these conditions, and this is not surprisingly from theoretical models appears to be centered around the location where our sun is. Okay, so it's not a big surprise. As I said, the issue is not settled, so we wanted to look into other aspects of this problem. This, as you see, is a table that summarizes some of the findings of the literature, and not all of them agree on whether all the galaxy is habitable or not. But we did this work some years ago, which opened, I would say, a new research direction, and there have been some follow-ups in the past few years. But the idea was to look about putting together two very different things. One thing is the habitability of the galaxy, and the other thing is the fact that at the center of the galaxy, we know that there is a supermassive black hole that releases, during its initial phase, released a lot of ionizing radiation. So during the initial phase of the accretion of the black hole, essentially you have an active galactic nucleus, and this is a source of huge radiation in all bands, but in particular very high energy. So we asked ourselves, what would be the implications for habitability of the galaxy? Would the galaxy be entirely sterilized during the active phase or not? Okay, so we looked into this, and we did this with some using inputs from theory and observations, and assuming that there was this very early stage that lasted probably less than 1 billion years at the beginning of our galaxy, where there were already stars in the galaxy and there were already planets in the galaxy, and at the same time the supermassive black hole was accreting mass near the Eddington limit, so with the maximum rate that is possible based on the laws of physics, and releasing a huge amount of energy. And we were trying to see what would happen to a rocky planet given a certain distance from this supermassive black hole. Okay, so the physics is well known. There is no big room for doing new models, because we know the physics of the black holes. We know how much radiation is radiated. We know how long it lasts, this phase. We know the spectral features. So we could put all of this in a machinery, and we could calculate what is the impact on the planetary atmospheres. And of course, if you want to do this in a totally coherent way, you should do a hydrodynamic equation, a coupled hydrodynamic equation to study the atmosphere of the planet and how this radiation interacts with the atmosphere. But we can use, and we used, and other people used, simple model, which is that there is a regime where the atmospheric loss happens only with one free parameter. Well, two free parameters. One free parameter is the input, the energetic input from the source, which in this case is the black hole. But this is something that was used also for other sources, for example, stars. Okay. But for the black hole, you have this flux coming from the black hole, and then there is this other parameter which is called epsilon, which is related to the efficiency of the process. So it's a number that can be estimated, and that tells you how much atmosphere you can lose when that much energy impacts on the atmosphere. And so we can calculate how much atmosphere you lose. And why this is important? Because if a planet has an atmosphere, and it's a rocky planet or a terrestrial planet, and it loses the atmosphere, then this, we can imagine, is not very good for life. Both because the climate of the planet will change completely, and also because the planet will be, the surface of the planet will be bathed in radiation, and in particular the ultraviolet radiation is very harmful for living organisms if it's not properly screened. And so, I mean, you can imagine that this may have consequences. So what we did was calculating where you have this mass loss given a certain distance from the planet, from the center of the galaxy. And if we found that actually the inner region of the galaxy, the bulge of the galaxy, is very strongly affected by this. And so, I mean, this is interesting because we made a point that you have to include this effect when you try to calculate the general model of the galactic habitable zone. This is another plot where we did the same thing, but as a function of time. So how much loss you have, how much mass loss you have as time passes. So this is a cumulative effect. Eventually you can lose even the entire amount of the Earth atmosphere during this process. So it's an important effect, given, of course, the distance of the planet from the central black hole. So just to give you an idea, this is the third column is 1 atmospheric mass of the Earth, based on some, different choices of the parameters. But in the most pessimistic case, you can lose one entire Earth atmosphere at 1 kiloparsec from the galactic center, which is, it's not a short distance. So we can say that there is a global effect. Of course, all of this is true only during the active phase. It's not true today. I mean, today we are not having this ionizing radiation coming from the center of the black hole, but, and also, I mean, we did some estimates on what would be the impact on life on a planet based on the amount of radiation that would be absorbed. And again, we found that there is an effect, but this is much more speculative because we don't know exactly all the details of how life in general can survive to a given radiation dose. Okay, this is a very complicated issue, but this is just to give some reference and to start thinking about this point. Okay, but as I said, I mean, today we don't have this effect. Let me go straight to another issue. What we did was to look at processes that can happen today, that didn't happen just at the beginning, but that can happen today and that can have an impact on life on other planets. And one that we explored in another paper is this process which is called tidal disruption events. Tidal disruption events, they are basically the destruction of a star that passes closest to a black hole. Okay, so when you have this central black hole, which I remind you that the central black hole. Sorry?
No, excuse.
The central black hole has a very big mass, millions of solar masses. Okay, so it's at the center of the galaxy, and around the black hole there are stars orbiting the black hole. And actually, this is one of the way we found out that there is a central black hole by studying the orbits of these stars. But from time to time, a star can pass very close to the black hole, and in passing close to the black hole, the tidal effect, so the tidal the effect of gravity has this disruption of causes this destruction of the star. And when this happens, all the material that falls into the black hole and goes around the black hole is heated, and you have, for a short amount of time, you have an accretion disk, precisely the same kind of process that we had during the active phase, where you have the black hole surrounded by an accretion disk. But this happens only for a limited time, and also it happens randomly during the entire history of the black hole. So you can have it today, or you can have it in 100,000 years. But there is a rate of events that is observed, and we know that it happens. And the typical rate is, in a galaxy like the Milky Way, is 1 every 10,000 or 100,000 years. And the typical duration of this disruption is 1 year. So we tried to look at this process to see, when there is this burst of energy, what is the effect of this burst of energy? And we found that if you make the cumulative effect of all these tidal disruption events happen over the history of the Earth, for example, 5 billion years, the cumulative effect is comparable to the one that we had at the beginning of the history of the black hole. Okay, so it's not a negligible effect. There is, based on these calculations, theoretically, there is a possible impact on the habitability. Of course, it depends on the distance. So it depends only on, it's probably important only for inner regions of the galaxy, but it is there. And this is the impact of TDEs compared to the AGN. There is a very similar effect, as I said. Okay, so this is a published paper. You can look into the details. But it's another example of the kind of things that one can do with these problems. I won't go too much into detail of the biological effect because, as I said, it's very uncertain, but we did estimates also these that you can find in the paper. Just as a short message, I mean, there may be an effect. And so we believe that, again, these kind of events can have an effect that goes all through the bulge of the galaxy. Okay, so in another paper, we looked in particular to the habitability of the bulge because, as I said, the inner regions of the galaxy, according to some models, can be completely hostile to life. But again, things are more complicated. You can imagine ways to have life surviving, for example, because if you have a terrestrial planet that has a very thin atmosphere, you can lose it because of the high energy processes and because of supernova explosions and so on. But if you have a very thick atmosphere, in fact, and you lose part of the atmosphere, perhaps this makes the planet more habitable than it was at the beginning. So there may be a balance between these two effects. So in this paper, we looked into a bunch of these effects. One effect was the supernova rate in the bulge to see whether actually there is a higher likelihood of complete sterilization of a planet or not, or mass extinction or things like that. And we found that, in fact, the inner region of the galaxy, the bulge, is a very difficult environment. There are many more catastrophic events there than there are here where we are. Our region is a safer region. But at the same time, it may be that they are not as harmful as one might think for different reasons. One reason is that the interval between one event and the other, on average, here we're talking about, statistical estimates, on average is short enough to have to give the planet time to recovery. And the other reason is that because the density of stars is higher there, it's true that you have more events, more catastrophic events, but you also have many more places where life can, in principle, appear. So you have, overall, you may have a constant, more or less constant probability of having an inhabited planet there. And also, let me get to something that of course, it's very, very speculative, but it's not as crazy as it seems, which is this topic of transfer of life from one planet to the other. Okay, the ratio behind this is that we know in the solar system for certain that there's been transfer of rocks from one planet to the other, for example, from Mars to the Earth. And in fact, people studying life in the solar system know that if you find life on Mars, then you want to be very sure that it's not a contamination of life coming from Earth on board some rocks that was traveling in space and left Earth and arrived on Mars. Okay, so this is certainly in the solar system, but there are studies, and there are many studies in the literature, reputable studies about the possibility that you can have this process also in interstellar distances. And if you remember what happened, I don't know if you knew about this, but we have this recent finding of at least 2 asteroids or rocks that came from interstellar distances that were observed in the solar system. So we know for certain that this can happen. And also all the planetary formation models show that there is a lot of mixing of material from one planetary system to others. Okay, so it's not entirely impossible that you have an inhabitable planet somewhere and that you have some rocks traveling, for example, for 100,000 years and reaching another interstellar, another system. And if life can survive in the rocks and there are protection mechanisms, then you can bring life from one planet to the other. So I'm not advocating this as a mechanism. I'm not saying that this is something that we know for certain that can happen. I'm just saying that it's interesting from a theoretical point of view to do some calculations and see what would be the chances of this happening really, and also to do experiments on Earth to see what is the survivability of organisms trapped in rock that can survive in space, for example. Okay, so we should consider this. And if you consider this, you see that the time scale would be in the center of the galaxy, because the stars are very close to each other. It's much, much easier for a rock to go from one star to the other. The distances are much smaller than here. So if you calculate the average velocity of these debris flowing around from one planet to the other, you can actually cover the entire volume of the bulge, even starting from one location in a short amount of time. Again, why I'm saying this, I'm not saying that this is happening. I'm saying that if you want to calculate what is the probability of finding life there, you don't just have to account for catastrophic events that can wipe out life. You may also want to account for events that can transfer life from one place to another, so increasing the probability of life surviving everywhere. Okay, so just to be clear that I'm not entirely convinced that this can happen, but it's an interesting theoretical perspective. So let me go to the final thing I want to discuss very rapidly. This is again another issue which is a bit technical, but it's related to everything we saw before. And this is a paper that we published last year with Claudio Grimaldi. I think it's a very interesting issue that I would like to outline. So as I said at the beginning, in the next few decades, we will have surveys of planets, exoplanets, and we will look for biosignatures. So we will try to see if there are indications that there is life on these other planets. So the question we asked is a question that is often asked very qualitatively, and we try to be instead more quantitative than usual. And the question is: suppose that we find a certain given. Suppose that we find evidence that there is life on another planet by biosignature. Okay, so suppose that we are sure about this. This is the hypothesis. What is the statistical impact of this new information? Okay, so we now know that there is only one place in the universe where there is life. Suppose that we find another one, okay, and that we are totally sure that there are no ambiguities, that there are no false positives. Of course, this will not be the actual case, but this is an ideal case, okay? Suppose that we know this. What this new information will tell us about the abundance of life in the universe. Because one problem is that because we only have one example now, we cannot actually do inference based on one single data point. It's very difficult, okay? It's basically impossible, okay? But if you have two, what can you say? And so to do this, we did this Bayesian statistical approach. Bayesian methods are, as you know, based on the fact that you have a prior probability and you upgrade the probability after having new evidence. So the prior probability is how much probability you assign to the fact that there is life elsewhere in other planets based on what we know now. And then you upgrade this initial probability, this prior probability, with the new data, which is we found life. Okay. So this is interesting because you can start from very different priors, because we know nothing at the moment, almost nothing. So there may be a pessimistic prior, which is we believe that life is very rare in the universe, it's only here on Earth. And then there may be an optimistic, which is, well, I think life is very common. So basically everywhere where there are the right conditions, life will appear. And so you can use some parameters to model this prior. What we did is we divided the issue in three probabilities. One probability is the probability of observing a planet. The other probability is the probability of detecting biosignatures. And these are probabilities that in principle we can calculate based on what we know already, okay? They are, the real unknown, the thing we don't know, is the abiogenesis probability, the last factor. We don't know, once you have a habitable planet, what is the probability that life will appear there? We don't know. So we want to upgrade this unknown. We want to start from giving, for example, an initial probability, which is, well, every time you have a habitable planet, there is life, which is 100%. This is prior probability. Or, well, only, I don't know, one every 10,000 planets where there is habitability condition, you will have life. And this is very pessimistic, okay? And so this is the exercise that we did. And we found that even just one more biosignature, even just one indication that there is life on another planet will change the probability in a very strong way, even if you start from a pessimistic attitude. So in other words, if you are very pessimistic and you find that there is life on another planet, then you are forced to upgrade your prior and to be much more optimistic than before, okay? This is, it's something that intuitively can make sense, but it's often confusing in terms of statistics. So we did this in a rigorous way, okay? And so the idea is we really have to look for these other biosignatures, because even just one will change completely the way we look at the diffusion of life in the universe. But, and there is a but, of course, we also asked ourselves, and this is related to what I said before, we also asked ourselves, okay, what happens if the origin of life on different planets is not independent? So we always think that life appears on Earth and then it appears on some other place, and these two processes are random and they are independent. But if there is panspermia, as I said before, and if it is an active process, then this is not true anymore, because if you have two close by planets and you have life appearing on one planet, then there is a higher chances that life will spread to the other planet, okay? If panspermia can work, we don't know that, but if can work, we have to be careful, because then it means that the statistical conclusion that we can derive would be lower. And in fact, we demonstrated this fact statistically, that you have, what I said before is true if you have uncorrelated process, but if they are correlated, the significance, the impact of the discovery would be lowered, okay? So that's why, again, we have to take this thing seriously and to decide whether we believe that panspermia can be possible or not. And in another paper that is not published yet, we are in the referee process, it's been accepted, but it's not published yet. We showed that actually, if panspermia is a process that can actually work, there are things that you can observe that will tell you that this is the case. Because if you do a survey of exoplanets, but this is something that we'll only do in the very long near term, but if you do a survey of exoplanets, you should find that there are correlations, okay? That there is an increased chance of having planets, inhabited planets around the location that is already inhabited, okay? So you can look for these correlations to try and detect the possibility, okay? Very theoretical and very, as I said, and very speculative, but we are theorists, so we try to have fun with these kind of things. Okay, so I think I can end here. In fact, I think this is more or less the things I wanted to discuss. As I said, I mean, it's a very much larger than issue than I described here, and I only showed some of my research interests. But I think that the conclusion is that there are many things that can be done. It's a very interesting topic to work at the moment. Then we know very little, so there is a lot to learn, and also it's exciting because we can talk to other scientists from different fields and learn new things and put everything together and try to get a better understanding of many of these problems. Thank you.
Thank you. Thank you very much. It's a very interesting topic that I would say very complex for its connection with other fields. Very interesting to me also the probabilistic approach to make the estimates. Is there anyone with the questions?
Yes, I have a question, a couple of questions. I'm Emanuele Fiandrini from Perugia.
Hello.
So the first question is there any general definition of life? This is the first question. What kind of life we are searching for? And the second question connected to this is there any search for a shadow biosphere on Earth?
Okay, first question, the answer is no, we don't have a general definition of life. There is many disagreement, there's a lot of disagreement about whether we should have a general definition, but at the moment we certainly don't have one that is universally accepted, simply because we don't have a theory of life. And to have a definition, you have to have a theory. So it's a complicated thing, and this is why I never mentioned life as something that we know. I just mentioned habitability, which is something that we don't know also, but it's a bit more general because it's related to preconditions of life, not life itself. So we want to have a pragmatic approach, which is we know what life does on Earth. We want to try and look if there is something doing the same things that life does on Earth. We know that there may be things that life can do, perhaps, that are not the same that life does on Earth, but we want to start from the things we know. And also, we don't want to just look, randomly, because the universe is big, and you want to focus the attention on places that are interesting, and that's why we have to have some criterion, and the criterion of the habitability is one possible criterion, and I'm not saying it's perfect, but it makes some sense. The example I make often is that suppose someone tells you that there is another planet with life in the galaxy. We'll give you this information. This is entirely 100% sure. You just have to find it, okay? You cannot find it. You don't have enough resources, observational resources, to find it completely random, okay? Because the galaxy is big. There are 400 billion stars, and there are probably more planets than stars, and so this would be almost, a blind search would be almost hopeless. Basically hopeless, okay? So we're not doing a blind search. We are doing a search on the vicinity of our solar system, because this is where we can look better. And we are looking for places that are similar to Earth. And I know that this is something like the old joke of the guy that misses the keys and he's looking for the keys below a lamppost. And someone tells you, but is it there where you missed the keys? And this guy says, no, but this is the only place where there is light, okay? And I know that is a similar situation, but this is the best we can do at the moment. So first answer. Second answer was whether we are looking for a shadow biosphere. Not personally, but people in the world, yes. I think it's something that is more related to biology, but yes, there are studies on this. And in fact, I can give you a simple example, which is not exactly a shadow biosphere, but it's something which has some similarity. We found Archaea, which is a third dominion of life. Basically, we found it in the past, 30, 40 years, something like that, if I'm not mistaken. And this was a huge discovery. No one knew about that, and it's everywhere. There are Archaea everywhere on Earth, and we didn't know. So I think it makes sense to look for a shadow biosphere. And it's complicated because if it's really a shadow biosphere, it's hard to find because we don't know what to look for exactly. So I think I mean the problem is already very complicated if we just restrict ourselves to what we know. So
okay.
Okay, thank you, Amedeo.
I see Maurizio Busto has the questions.
Yes, thank you. Thank you for a nice seminar, very interesting. Coming to this last subject you touched now, to have a biosphere similar to the one that developed in the solar system, it is commonly believed, not an expert, but that an important
I'm missing the...
Yeah, I'm missing too.
We lost you, Maurizio.
you don't hear me?
No, now
Oh,
yes.
yes.
Until you said we know that, but then I don't know.
Sorry. Probably was an important point is the fact that the material in the solar system was differentiated.
Mm-hmm.
That is, underwent heating periods
Mm-hmm.
in which the materials could move chemically or for their physical properties. For example, in the Earth, the metals went to the center, no, and differentiated from more refractory materials that are those that form the Earth crust. In the solar system, the process of differentiation was strongly helped by the fact that the solar system had a huge amount of aluminum-26 in its composition, 5 × 10⁻⁵ with respect to aluminum-27, which is about at least 10 times the average in the galaxy revealed by gamma ray observations. So one might even speculate, I'm not saying that, I don't know, it's just to make an argument, one can even speculate that life exists only here, because this enormous excess of aluminum-26 was necessary and does not exist as well, or maybe it exists.
Mm-hmm. Yeah, I think I got the main point, and I again, the problem is that there are so many factors that, in principle, can be included in the estimates of the probabilities of life appearing, that it's really hard to have a deterministic approach to this kind of thing. And the complication, and of course, I mean, there are many studies about what makes a planet habitable, and there are for example, that there is this rare Earth hypothesis, which is that if you look at all the factors that made the Earth as it is, the chances that this process happens elsewhere are so low to be almost negligible, because there are, and of course, I mean, if you go into even more details, as for example, I didn't know this problem of the aluminum, but there are many others, because, for example, there are studies about the abundance of isotopic elements, which perhaps are needed for internal heating, and there are many different. You can complicate this thing at will, and things get only worse, because, as we know, the probabilities have this feature that if you multiply probabilities, each new factor reduces the overall probability if they are uncorrelated processes, okay? So every time you find a new process that has some probability, you have to multiply that factor by all the others, and that kills the final result. So I think that if we approach the problem in this way, there is really few hope that there is another place where there can be life elsewhere.
You are right.
Yeah.
This is my impression. Thank you.
Yeah. Okay. But I think that there may be a more hopeful approach, or more pragmatic approach, and saying we actually don't know, and we look around, because we cannot decide this thing just based on statistical arguments. We have to decide it empirically, and so we look around and we decide. Okay, and this is why I never subscribe to any position, because sometimes people say, I'm sure that life has to be abundant in the universe because there are so many planets out there. It would be absolutely impossible that we are alone. And I say, no, it's, you know, it's probability. It can be. There are low probability events happening all the time. And here we are. And even, you know, even if it's a very low probability, here we are anyway. So it doesn't change the thing from our point of view, okay? But at the same time, I cannot say that I'm sure that life is rare, because we simply don't know. We have to look, okay?
Okay. Gianluca?
Yeah, hi. So I was wondering, because there is this famous Fermi paradox, right? In which he was saying, where is everybody? So somehow it's badly posed, or it's not correctly addressed?
No, it's well, there is a literature on the Fermi paradox, and there are also people who say that it's not a paradox, but the main point of the Fermi paradox, I think, is interesting. And the main point of the Fermi paradox is that we have no evidence that there is life elsewhere in any way. So not just, you know, aliens visiting Earth, which is what most people would believe, but even, you know, just by looking at radio signals or astronomical observations, and so we have no evidence. Okay, and it is a bit surprising, because if life was spread very commonly everywhere, then probably we should have found some evidence much easier than this. Okay, so I don't know. I mean, at the same time, I think that again, as many of these arguments, it's interesting because it's food for thought. But I think we do science not just by thinking, but we do otherwise we would be philosophers. We do science by having you know, empirical evidence. So we just have to keep looking, I guess.
Thank you.
Thank you. Marco Madami has a question.
Yes, I think there was another question before mine in chat.
Yeah, there's another guy. Yeah, Andrea Parpignan.
Hi, good morning or good afternoon. And I would like to ask to Amedeo, as you said, the icy worlds, for example, are planets where could be life, or I mean, life could form, but they are not in the habitable zone because there are a lot of criteria to consider and to include. For the same reason, does exist a theoretical model that, for example, does not include Earth in it? Like the habitable zone is somewhere else, and the Earth is the icy worlds of today.
Yeah, that's an interesting question, because if you think about what we were saying before, and if you think, for example, that Earth as itself is a very strange place with a very rare situation, it may be that the most common place in the universe where you can find life is not a planet that is similar to Earth. It may be that Earth is a bit of a freak, where you have these you know, planet covered with water, with an atmosphere, and with, you know, the biosphere that surrounds the whole planet. But this is basically it. It's one of the very few places. So it may be, for example, I don't know if I interpret correctly what you're asking, but I guess that one point to put it is, it may be that, for example, icy worlds, let's think about icy worlds. It may be that icy worlds are much more common. In fact, we are probably reasons to believe that icy worlds are much more common than planets like Earth. And if they are habitable, it may be that most life would be in this kind of places. And this is interesting also for the previous question, because if this is the case, then you would have a universe, a galaxy with many places where life is, but it's but there are places where life is not visible. You cannot have any evidence of that, because if you have life below a thick shell of ice and you observe it with the telescope, you cannot find evidence of that, or it's very difficult to find evidence of that. So it may be that life is completely different. I mean, that there is no reason why life should be as the planet Earth. It could be that life, that the most abundant form of life is some microscopic life living in icy worlds, and that they have no way of being manifest outside. Okay, so yeah, maybe we would be very, very unlucky in that case, because we wouldn't find any evidence probably. I have a student right now working on this problem of the icy moon to see to do theoretical models on icy worlds, because you can have icy worlds in a very different set of situations. You can have, for example, not only the moons of giant planets, but you can have a planet like Earth that has an ocean initially, then it gets frozen because, for example, the star changes luminosity, or the planet is moved to another orbit, and so it gets frozen and it maintains an ocean. Okay, and this is an example. For example, there are many situations where you can have that. So, but you can have planets around brown dwarfs, for example.
How can life move through the ice?
No, it doesn't move in the ice. It moves in the water that is below the ice. So the model. I didn't say it very, very clearly, perhaps, but the model is that you have a thick layer of ice. Then you have this ocean, which in the case of Europa, for example, is 100-kilometer ocean. Okay, so it's a very deep ocean. And then you have an inner source of heat where you have also volcans, and so you may have chemical activity. Okay, and so I mean, if you look at what happens on the oceans, on the floor of oceans on Earth, this is something that can happen. You can have some ecological niche that lives in these hydrothermal vents. So why not?
Yeah, interesting.
Yeah.
Then Marco.
Yes. Okay, thank you very much for your beautiful talk. And I have a question which is maybe a little bit out of topic, but since you are also a science communicator and not only a scientist, and also a popular one, I would like to ask you, what hints would you give to a student who would like to start his career in science communication? And what is your general opinion about the need of a good science communication today, in our society, where information is so widely available, but also easily manipulated by those who want to discredit, for instance, science? And we know this is an issue. So what do you think about it?
I think it is a very important topic. I think we should be, as scientists, very active in this thing. Not too much active, because I think that being too much active is also not always a very good thing, because we have examples of situations where too many voices don't improve the conversation, but only make it worse if they are not well prepared in doing this kind of work. And for this reason, I think that some aspects of them are better left to professionals. And now, fortunately, there are in Italy a number of places where one can become a science communicator if this is what is what the main idea behind the career is. Okay, so if one wants to become a science communicator, there are schools and places where one can learn the professional skills that are needed for that. But a different thing is if you want to simply be a scientist, keep doing science, and also have communication activity, and this is something that you have to do in parallel, and not everybody wants to do that, and not everybody has the energy to do that, and also the skill to do that. So about this, I don't have any general advice, actually. I think if one wants to do that, probably they will find a way, they will figure it out. But if they want to do that professionally, they should decide very early to perhaps to go to one of the schools of science communication that exists in Italy.
Thank you.
Thank you. There are no other questions. It's okay. It's time to thank you, Amedeo.
Okay.
We cannot make claps or so. Yeah, we are on Zoom. But it was a very brilliant talk and very super interesting subject.
Okay.
So thank you.
Thank you.
I thank also all the participants. And I just recall we have other seminars in the next. The next is on next Friday, I think. Yes. So see you for the next. Next Friday.